Okay, so let's get started. And we'll start with a summary from, let me start with an announcement first. Assignment 2 is now available on the web, and it's due a week Friday. The solution for assignment 1 is now posted on the website as well, on the same section as the assignment itself. It was a relatively hard assignment. I haven't marked them all, but I hope to finish by today. Part of this was to assess the level of the students in the class, so I do realize it was a pretty tough assignment. But in general, you should expect the assignments that they will take several days to do. So I expect to have the solution, everybody's marked by today. The solutions are up if you guys are interested in looking at them. And assignment 2 will be due next week. So let's get started with the summary from last time. So if you recall, we had found the principle of virtual work. For statics problems, we had found that the total virtual work, which could be written as the sum of a generalized force and a virtual displacement of the generalized coordinates, was equal to 0. And because the coordinates are generalized coordinates, this is true no matter what variation in the coordinates we use. And so this gave us that the generalized forces were identically 0 for a statics problem. And the generalized forces were given by the sum over all the forces, the real forces, the external forces, I, dotted with the derivative of the vector of where those forces act, divided by Qj. And so that was the realm of statics. And then for dynamics, we have D'Alembert's principle, which is based on the idea that F minus MA equal to 0. And if you recognize and introduce this new force called the inertial force I, then D'Alembert's principle says that we can treat dynamics cases the same way as we do statics cases, but just by introducing this additional force I. And so then the idea was to apply the principle of virtual work to the new forces F plus the inertial force I, and set that equal to 0. And so then we did a lot of math to convert the term with the I, the capital I in it, to also be in terms of the generalized coordinates. So the term with the capital F just turns into the term we have above here with the generalized forces Qj. And the term with the I, we found, ended up turning into a term with the kinetic energy. So this thing here, the sum of the inertial force I dotted with the delta Ri's. So there's an inertial force I for each mass I with its own acceleration I. We found that this term here could be rewritten after a lot of manipulations into minus the sum from j equals 1 to little n, so the sum over the generalized coordinates of d by dt times di capital T by di qj dot minus di capital T by di qj delta qj. So I ran out of the page there. Where we introduced this kinetic energy, T, to be the sum now over all the particles from I from 1 to n of Ti, where Ti was a half mi Ri dot squared. And so putting everything together, we found this form of D'Alembert's equation d by dt of di by di qj dot of capital T minus di capital T by di qj was equal to qj. And that was the more useful form, but in more insightful form of D'Alembert's principle. Where T, capital T, we can recognize as the total kinetic energy. And then we also sort of compared by inspection this boxed equation and noted that it looked awfully similar to what you get from the Euler-Lagrange equation when you try to find the stationary value of some function. Okay? So any questions about that? Okay, so one little thing that, so let me go back first and make a comment. Our goal, remember, here in analytic mechanics is to remove the need for vectors, right? So we introduced this concept of generalized coordinates and generalized forces, and then we find that we can write equations that are equivalent to Newton's second law using only scalars. And so this boxed equation here uses only scalars, right? Qj, the generalized force, is a scalar. It's calculated from vectors, but ultimately it's a scalar. If there's another way to find it using just scalars, then our job is done, and we'll see that that's possible. The kinetic energy T is, of course, a scalar, and the generalized coordinates can be used independently. So one thing that I swept under the rug here is that the T is still expressed in terms of the Ri dots. So I just hid away the fact that, in fact, this does not fully complete the problem, or at least it might not, if you can't write the T in terms of the QJs. The kinetic energy has to also be expressed in terms of the QJs, because right now it's expressed in terms of the Ri dots. Okay? So let's just convince ourselves that we can write the kinetic energy in terms of the Qi dots and really get rid of the R's. So let's show T of the Ri dots can be written as T of the Qj's. And what we'll see is that, in fact, the Qj dots, in most cases. So the total kinetic energy T was the sum from I equals 1 to capital N of a half mi Ri dot squared, where m is the number of particles. So if we write this out explicitly, it's the sum of I equals 1 to n of a half mi, and then it's dri by dt dotted with dri vector by dt. And so let's just do our general procedure for converting r's into q's, right? So recall that we can write dri by dt as the sum from j equals 1 to n of dri by diqj, qj dot, plus the last term dri by dt. Alright, that's something we wrote in the first or second lecture. So I plug that in twice. So T is equal to the sum of I equals 1 to capital N of a half mi. And now we're just going to write that sum in twice, right? So we have the sum of j equals 1 to n of dri vector by diqj dot plus dri vector by dt. It's multiplied by a second sum, so we have to change the index, so let's just call it k, from k equals 1 to n, dri by qk dot plus dri by dt. Alright? And so you could write it out, or you could look at it for a little bit, and you can see that there's a lot of cross terms, but there's three kinds of cross terms, right? And so let's group them together very generally. So the first cross term that we're going to get is going to mix qj dots with qk dots and have a sum over I in it. So ultimately we'll be able to write it as a sum of j equals 1 to n, a sum of k equals 1 to n, some coefficient which we'll call ajk, qj dot, qk dot, plus a second sum over, let's say, the k's, k equals 1 to n of bk times qk dot, and then plus a term which we'll call c that doesn't have any qj dots or qk dots in it. Alright, so there's the terms that have two q dots in it, there's terms with one q dot, and then there's the other ones. Alright? And so ultimately, maybe now you're convinced that we can indeed write the kinetic energy as a function of the generalized coordinates and their time derivatives. That is the absolute most general case, right? Now things simplify a little bit if the coordinate transformations don't depend explicitly on time. So if the Ri, which you can write as a function of the coordinates, if that does not depend explicitly on time, and note that this is not the same as the total differential divided by dt. Because of course, the total differential, the time derivative of the total differential is not 0 because the particles potentially could move. But the coordinate transformations don't depend on time. That means that the second term in the sum, that the Ri by dt, is equal to 0. And so that simplifies the kinetic energy considerably. And then the only term that we're left with is the first term. And this is what's true in most cases. That T will have the form of a sum from j equals 1 to n, k equals 1 to little n, of ajk times qj dot qk dot. So for example, in Cartesian coordinates, where we have q1 is equal to x, q2 is equal to y, q3 is equal to z. The kinetic energy T of a particle is a half m x dot squared plus y dot squared plus z dot squared. And so what we find is that the let's write it with the same indices. The ajk is equal to a half m qj dot squared times delta jk. Where delta jk is what we call the Kronecker delta. And that's equal to 1 if j equals to k, and 0 if j is not equal to k. I can make that delta look a little bit nicer. Okay. And so in the particular case of Cartesian coordinates, you get the x dot, the velocities squared with themselves, and there's no cross terms. If you do this in polar coordinates, you'll see that you'll have a cross term, and that's one of the questions on the assignment. And you'll see that there's an r dot theta dot in assignment 2. Okay. So hopefully I've now convinced you that you can indeed write the kinetic energy in terms of the generalized coordinates, and so that D'Alembert's principle with the d by dt's of the total kinetic energy, that whole equation, only depends on the generalized coordinate. And so we've achieved our goal. Okay. So let's do an example. of applying this. Or is there any questions about that, the kinetic energy? Okay, so let's do an example of using D'Alembert's principle for a very simple case and see that it is in fact equal to Newton's second law. We know it has to be true always. So this is going to be example 3.6 from the notes. And let's use D'Alembert's principle to find the equations of motion for a particle in a conservative field. What do we mean by a conservative field? We mean a field that gives a force that on a closed loop exerts no work. So examples of the conservative fields that you're familiar with from undergraduate physics are gravity, right? The field of gravity, or the force from the field of gravity, does no work, no net work, if you move a particle around and back to its starting position. Another example is the Coulomb force from the electric field. There's no net work on closed path. Okay, and so you're going to remember from undergraduate physics that when you have a conservative field or a conservative force, the force can be written as the gradient of some field. So what this means is, in general, we can write the force F to be minus the gradient of some potential. Okay. So phi we call a potential. So for example, gravity. Or Coulomb potential. So I hope that this is not anything new, that it's possible for a force to be written as the gradient of a potential. Okay. So let's consider one particle in Cartesian coordinates that is subject to a force from this potential. Okay. So for a particle, so our system is only one particle. So for one particle, T, and we're using kinetic Cartesian coordinates, so the kinetic energy of the particle is a half m x dot squared plus y dot squared plus z dot squared. All right. And remember, we want to use D'Alembert's principle, which has the thing on the left that looks like the Euler-Lagrange equations with all the partial derivatives of capital T, and on the right-hand side, we have the generalized force. So we need to figure out the generalized force. So Qj, using our equation for the generalized force, is the sum from I equals 1 to n of the force dotted with di Ri by di Qj. All right. So now we have Q1 is equal to x, Q2 is equal to y, and Q3 will be equal to z. That's our choice of generalized coordinates for Cartesian coordinates. Capital N is equal to 1. We only have one force, or one particle, right? So after the net force on the particle, and there's only one particle. So let's calculate the generalized force that comes from a force that's given by the gradient of a potential. So Qj is equal to oh, let's write, sorry, let's follow the way we do it in the notes. Let's write the vector r, the position of the particle, as x times x hat plus y times y hat plus z times z hat, right? So that's the position vector in Cartesian coordinates. So now let's calculate Q1, which is the same as Qx, right? So that's j equals 1. And so Qx is given by f vector dotted with di ri, but I'm going to drop the index I since it only goes up to 1, divided by di x, right? So the vector f, the force f, well, let's write it this way. So that's equal to the force. Let's leave the force and we'll put the potential in a second. So that's the force F dotted with di r by di x. If you look at the vector r, the only term that depends on x is the first one, so that's x hat. So it's F dotted with x hat. And so that gives us the x component, oops, there's no vector anymore, the x component of F. Okay. So now the x component of F is given by minus the potential di phi by di x, since the force vector F is minus the gradient of the potential. That means that each component of F is di phi by di of that component. Okay? And so similarly, for the other coordinates, we get that Qy is minus di phi by di y, and we get that Qz is minus di phi by di z. So D'Alembert's equation was that d by dt of di capital T by di qj dot minus di capital T by di qj was equal to qj. So let's do this for j equals 1. So x so we have d by dt, and now we want to take, well, let's just write it out explicitly, di capital T by di x dot minus di capital T by di x, and that's got to equal to qx. So remember that T is a half m times x dot squared plus y dot squared plus z dot squared. So di T by di x dot is equal to mx dot. Right? The y dots and z dots don't depend on x dot, so the derivative of a half mx dot squared is mx dot. The derivative of the partial derivative di T by di x, T does not explicitly depend on x, so that's equal to 0. And so if we put this all into D'Alembert's equation, we get d by dt of mx dot equals the generalized force on x, which was minus d phi by dx. Right, that was equal to fx. So d by dt of mx dot, m does not depend on time. So what we get is mx double dot equals minus di phi by dx. And we know that minus di phi by dx is the same as fx, right? And so in fact, using D'Alembert's principle, we've recovered Newton's second law. That's the x component. So we've essentially used only scalars and re-derived one of the components of Newton's second law. We did use a vector r when we calculated the dot product of the applied force F with di r by di q. But as you'll see, once you get practice, you won't need to write the thing out as a vector at all. And so, of course, if you do this for y and z, you end up getting the same equations. Oops. I'm losing control of the tablet here. It's not the internet connection, it's the tablet. Okay, so just for fun now, so we've solved the problem, and we've shown that D'Alembert's principle gives the same answer as you would expect from Newton's second law. But in a much more abstract way, right? If you wanted to do Newton's second law properly, you would probably have to do a diagram, draw the forces, etc. So you can see how this is converging to a much more potent way of doing things. So let's do just for fun, because this will be useful in a minute. Let's create a new quantity, L, and we'll define it to be T minus phi. All right? Where phi has the same meaning. And let's ask ourselves, what is the condition if we define a new function s to be the integral from, let's say, 0 to t of L. Call this the action what is the condition for the action to be stationary? And we'll see that this quantity, which we call L here, will eventually start calling the Lagrangian. Okay. So we know from the Euler-Lagrange equation that if the action, so this integral of L, is stationary, then the function L must obey the Euler-Lagrange equation, right? So the Euler-Lagrange equation, if you remember, was that d by dt of di L by di Q dot, okay, minus di L by di Qj is equal to 0. In the case of no constraints, right? In this case, we're not imposing any constraints. So if L is t minus phi, then what we have is that d by dt of di by di Qj dot of t minus phi minus di L by di Qj, or sorry, let's plug in the t minus phi there as well. Now, phi does not depend on the Qj dots. In certain cases, so let's say we're restricting ourselves to gravity. So if di phi by di Qj dot equal to 0, that means that this term will fall out. And similarly, if di t by di Qj is also equal to 0, which is the case that we had, that means the term with the t in the second term is 0. Then we find that d by dt of di by di Qj dot of t is equal to minus di by di Qj of phi. And of course, this is the exact equation that we had before. And it gives us back Newton's second law. So we've seen that, in principle, it looks like one can create this new function called a Lagrangian of t minus the potential, and then the equations of motion are given by the requirement that the action, so the integral of L dt, is stationary. And that's true in the case, at least the case that we've done here, when the potential does not depend on the Qi dots. So that first red line with the red arrow was 0, and also when the potential energy T does not depend on the coordinates themselves. So for that sort of special case, although most cases fall into it, we see that requiring that the action be stationary gives the equations of motion. And that, so this here is the same as above. In fact, this is also very important. Principle of mechanics, this requirement that the action be stationary is called Hamilton's principle. And we'll see it again in the next chapter, but this is just to give you a flavor of what's to come next. Okay. Any questions about that? So now let's look at how conservation of energy arises from D'Alembert's principle. So let's restrict our case again to when we have conservative forces. So our forces, our applied forces Fi, will be given by the gradient of some potential Vi. And so that means that they can be written in the form of minus di Vi by di x. That would be the x hat component plus di Vi by di y times the y component, di Vi by di z, the z component. Okay, so let's consider only the case of conservative forces. So the virtual work done by such a force that's the sum. So there's n particles, and they each have a net force that's given by a potential. So the total virtual work on the system is given by those forces dotted with the virtual displacements. Based on our definition of force, that is the sum from I, so minus the sum from I equals 1 to capital N of the gradient of a potential Vi dotted with delta Ri. So if you write that out explicitly, it's minus sorry, I'm trouble zooming in and out here. Okay, so that is minus the sum from I equals 1 to capital N. So writing out the vectors explicitly, so that's di Vi by di x hat, plus di Vi by di y hat, plus di Vi by di z hat, and that's dotted with delta of the vector r, which was, as we saw in the previous example, is x times x hat plus y times y hat plus z times z hat. Okay? So if we take the variation, so consider a delta x hat. X hat doesn't change, and so that's equal to delta x. Or if you take the product, the scalar product, right, you have a di Vi by di x hat, dotted with x hat, or delta x hat. So the x hat dot product equals to 1. And so you're left with the delta x. And so that, if we now do the dot product, right, from this line to the next, we're left with minus the sum I equals 1 to n of di bi by di x, delta x plus di bi by di y, delta y plus di bi by di z, delta z. And so this is the total variation of the VI with respect to the x, y, and z. Right? So that's equal to minus the sum of I equals 1 to n of the delta VI. Right? If you want to expand the variation of a function v as using the chain rule as the sum of the variations of the thing that the function depends on, then you get the line above it, right? So here we're just recognize that that's that expansion, and then we can write that as delta VI. So the conclusion is that the net virtual work here is equal to the sum of the net changes in the potential. So that makes sense, right? Energy perspective, if the potential is a potential energy, then the net work done is the sum of the changes in the net potential energies. So rewriting D'Alembert's principle now. So D'Alembert's principle we can write as the sum of I equals 1 to n of Fi dotted with delta Ri minus the sum from I equals 1 to n of the Mi Ri double dot dotted with delta Ri. Right? This second term here is what we were calling the inertial force. Right? So this is just Newton's second law, or the principle of virtual work applied to Newton's second law. Right? So that's D'Alembert's principle, but now we write in what we just found for writing in the case of a conservative force, that first term can be written as the sum of I equals 1 to n of the virtual potentials, delta VI, plus the second term. And for legibility, I should get back to it. The minus sign disappeared because there's a minus sign in front of the delta VI at the top here, right? And so if you, well, since it's equal to 0, I'm free to choose whatever sign I want. So I might as well make the both positive. Okay. Let me highlight that. It might not be obvious when you follow it in the notes. All right. So now let's consider a special case. Oops, I meant to go back. So remember, delta R's are arbitrary variations in the vector R. The virtual displacements that are in harmony with the constraints, but they're not necessarily in harmony with how time goes by, right? So we're allowed to displace the system in a way that, we don't push particles through walls and things like that. but we can push them in a way that that's not the way that they would go if we let time flow, right? But we can choose a particular case of a virtual displacement that's in line with the true displacement. So let's consider the case when delta r I vector is equal to dri. So we consider the virtual displacement that is in harmony not only with the constraints, but also with the passage of time. We're free to do that, right? The displacement is arbitrary, so we can choose whatever we want. So we should be actually a little bit more careful when we choose this particular case. So what we're more interested in, of course, is the generalized coordinates. And what we really want is when delta q equals dq. Okay. So if we choose the case where delta q equals dq, does that necessarily mean that delta ri is equal to dri? And the answer is no. And we know the answer is no because in the q's, which are independent from each other, we were always able to vary them independently. But we know that we're not allowed to vary the r's independently. So there's no reason to think that one particular choice of variations in the q's is equivalent to a variation in the r's. Right? So it's generally not true that delta, if you set delta q equal to dq, that you'll get delta ri equal to the dri. Right? That's generally not true. So this is only true in the scleronomic case. So delta q equal to dq implies that delta ri equals dri only in the scleronomic case. So what was the scleronomic case? The scleronomic case is when the transformation equations from the ri's to the q's do not depend explicitly on time. So the scleronomic case, remember, if we write the ri as a function of the qi's, if that transformation does not depend explicitly on time, we call that scleronomic. And that was in our first or second lecture. In that case, then delta q equals to dq does imply that delta ri will be equal to dri. Otherwise, if di ri by di t not equal to 0, so the transformations depend explicitly on time, then di q equal to dq does not imply that delta ri equals dri. And you can always, this is always very abstract, but you can always think of the vector r in terms of Cartesian coordinates, right? So the q's could be the Cartesian coordinates, and that those are generalized coordinates in most cases if there aren't any holonomic constraints. So if the vector r depends only on x, y, and z, and not on time, so your coordinate system is the traditional fixed coordinate system, that any change in one of the coordinates is directly a change, that same change in the vector r. But if the coordinates themselves depend on time, maybe it's a moving reference frame, Cartesian coordinates, then you can see that a change in the coordinates does not necessarily equal to the same change in the position vector. Okay, so these Q's, if you have trouble thinking about what Ri is in terms of the Q's, think of it in Cartesian coordinates. The vector r is independent of the coordinate system, right? It's the position of some particle. So if you introduce an origin, then you can write, and a set of coordinates, then you can write that vector r as a vector in a specific set of coordinates, for example, Cartesian. So let's consider the scleronomic case, all right? And furthermore, let's consider how this delta Q equal to dQ, so setting the virtual displacement Q equal to the true displacement dQ, how that affects the potential. And that's the same exact point if we have the potential V. So remember we had the VI's, which were each force was di VI by di x, right? So it's the potential that gives rise to the forces. So we can write this potential in terms of the generalized coordinates. And if dV di V by di t equals 0, so that the potential does not explicitly depend on time, then we also find that if we set the delta Q equal to the dQs, that means that the delta V's will be equal to the dV's. So the rest of the derivation, so we will continue assuming a scleronomic system, so that's the funnest word to write. Scleronomic system with a potential that does not depend on time. So that means that di V by di t equals to 0. So going back to our equation, we had the sum of I equals 1 to n of delta VI plus the sum of I equals 1 to n of MI RI vector double dotted with delta RI. Okay, that is D'Alembert's principle. All right, so that's going to be our starting point where I've already replaced the force, the F dot delta RI, with the delta VI. All right, so now we want to take the case. So in the scleronomic case where the potential does not depend explicitly on time, if I choose the delta QJs to be equal to the dQJs, then in that case, the delta RIs will become DRIs and the delta VIs will become DVIs. Right? So this now goes to the sum I equals 1 to n of DVI plus the sum I equals 1 to n of MI RI double dot vector now dotted with DRI vector. same thing with the deltas instead of D's instead of deltas. So that's equal to, I'm going to leave the first term unchanged. I'm going to multiply the second term by dt over dt, right? That's equal to 1. So the first term is unchanged. I equals 1 to n dvi plus. Now I can move the dt's around. So the one that's underneath, I'm going to bring this dt here underneath the dri, so that I have dri, I have ri dot. So that's the sum of I equals 1 to n mi ri vector double dot dotted with ri dot vector dt. A little bit of mathematical trickstery there. Okay, so continuing, that the first term is the same, I equals 1 to big N dvi, plus sum of I equals 1 to n. Now, this mi ri double dot dotted with ri dot, I could rewrite this whole term as a half m d by dt of ri dot squared dt. Okay, that's similar to what we did last time. So if you expand that derivative out, you'll see that we get exactly what we had. And so now I'll cancel the dt's again. I'm done using them. And I get I equals 1 to n of the dvi plus sum of I equals 1 to n of a half m d of ri dot squared. And the differential of ri dot squared is unchanged if I multiply it by a half m, so I can bring the half m inside. So the sum I equals 1 to n dvi plus sum I equals 1 n of d half m ri dot squared. And I guess at some point down the line I forgot that the m's also have I indices on them. Right. And so this thing here, of course, is equal to Ti. The kinetic energy of particle I. So this whole thing here is equal to the sum of I equals 1 n of dvi plus sum of I equals 1 to n of dti. And now I can bring out the d and interchange it with the sum, right? The differential and the sum are commute. And so I can write that as d, the sum of I equals 1 to n di plus d, the sum equals I equals 1 to n ti. Now, if I let the sum of the VI, so the sum of the potential energies of each particle equal to V, or the sum of the potentials associated with the force applied on each particle equal to V. And similarly, the sum of the potential and of the kinetic energies Ti to T, right? Then then I can write that as d of v plus dt, or d of v plus t. And so remember, this is all D'Alembert's principle. Oh, sorry, there's a question from Michelle. Oh, why? But then, okay, it seems like you figured out the... Okay. So this is D'Alembert's principle, right? So the total, the virtual work there, which we just calculated in a different way for the specific skleronomic case where the potential does not depend on time, this whole thing still has to equal to 0, right? So if the whole thing is equal to 0, so the differential of something equal to 0, that means the something is constant, right? And if you wanted to write it as an integral, so the integral of that, which is v plus t, is a constant. Right, so let's call that constant E. And so V is the potential energy of that's associated with the forces that are the conservative forces that are applied, right? We saw that the virtual work was that total net virtual work was the net change in potential from each force. So that V truly is the potential energy. So V is the potential energy of the system associated with all the conservative force. T is the kinetic energy. And so this V plus T, the potential energy plus the kinetic energy, is equal to a constant. Well, that's called conservation of energy, right? And so what we find is that E, which you might as well call total energy, is equal to a constant if the potential does not depend on time, and if the coordinates don't depend on time. And so that's actually a very powerful statement, right? Energy is conserved. We didn't make any assumptions, we just did the math, and we found this quantity, total differential is 0, and so that quantity must be conserved. And then we know from our knowledge of undergraduate physics that this V is just the potential energy and the T is the kinetic energy. So we effectively found that energy is conserved. And we had to make a mathematical restriction on that in saying that the potential must not depend explicitly on time. So we found that this potential energy plus this kinetic energy is a constant if the potential doesn't depend on time. So, think about it, right? If you have a particle moving around in gravity, you know that energy is conserved. But if you have some knob that changes the force of gravity with time, then you may not expect that energy be conserved. And so you might have, seen this in past classes or heard about it that conservation of energy is associated with the laws of physics not changing with time. And we'll go into that in a couple of chapters more deeply, but you can already see here that we have this connection between something changing with time or not changing with time, implying that energy is conserved. And as we go deeper into the analytical mechanics, we'll have more abstract things that are conserved, but we'll find that in specific cases where here B we could associate with the potential energy and T we could associate with kinetic energy, recover sort of our familiar undergraduate laws of physics, in this case namely that energy is conserved. Okay, so it's quite beautiful, right? Because when you wrote those equations down, you didn't think we were going to end up with something so pretty as a T plus V equals a constant. So that's sort of quite nice with this framework. Now, the last subject of this particular chapter, I think I will skip it. It's not super interesting, but let me tell you the gist of it. The gist of it is if you're in an elevator on Earth, you feel gravity and the elevator is stopped. And you may realize, or have thought about it before, that you actually can't tell if you're in an elevator that's stopped and on Earth, or if you're in an elevator that's in free space but accelerating upwards with the force of gravity. And so the next section in the notes covers the formalism for understanding that and associating this force of gravity with an inertial force. And it shows you how the two cannot be distinguished, and that if you're in an accelerated frame of reference, there are apparent forces that are related to the motion of that frame of reference. And it's one of the things that we don't have time to go into this course, but the fact that that inertial force depends on your mass, and that mass is the same mass that appears in the force of gravity. There's no reason to, right? The force of gravity is proportional to something we call mass, and then Newton's second law also has a thing that we call mass that's related to our inertia. There's no deep principle a priori that makes those two m's be the same m. Right? It's really, one is related to inertia, and one is related to generating this potential energy that we call gravity. And so it's a fundamental principle of mechanics, it's called the equivalence principle, that those two m's are indeed the same. And that's the very deep connection that Einstein realized when he came up with the general theory of relativity, so the generalized theory of gravity. A lot of the formalism that we develop in this course just carries into general relativity. And general relativity kind of just falls out of it, and it even doesn't seem like that genius of a leap, although of course it is. So since this is the end of the chapter, well, we'll technically go off another 5 minutes, but time-wise. But I think this is a good stopping point to talk about the Lagrangian on Wednesday's lecture.
Yeah,
Okay.
I'm kind of a
Michelle, you have a question?
On page 49, equation 3.30, in lecture today, you introduced the Kronecker delta. How did you get the Kronecker delta involved there? You know, we did the kinetic energy equals 1/2 m times x dot squared plus y dot squared plus z hat squared, and then you went AJ, and I couldn't quite read the other thing that you wrote, equals 1/2 q dot j squared, and then the Kronecker delta. How did you get the Kronecker delta in there?
Oh, here. No, okay, sorry, I was talking muted. So I rewrote the equation correctly. That was a little bit of a mistake the way I wrote it down the first time. So I actually just compared by inspection the form, which I'll label 1 here. I compared that with this. I compared 1 and 2. right? And so then I decided what AJK should be. So the Q's are the X, Y, and Z. So if I look at the term with the X's, for example, the first term, I see that I have, well, let me write it out explicitly. So I have, the first term is a half M X dot, right? That's the term that should be equal to a half M Q1 dot, that's the same thing, and that's got to be equal to the term A11. And so what I notice is that in the form equation 2, I don't have any cross terms. So I don't have any X dots with Y dots. I only have X dot squares, Y dot squares, and Z dot squares. So if I look in equation 1, in principle, it's allowed to have a cross term, right? The most general way of writing a kinetic energy could have a term in it that's X dot times Y dot. I don't see any X dots, Y dots. I only see QIs with QIs. So I find that J, in this particular case, the Cartesian coordinates, J is always equal to K. There are no terms where J and K are different. And so the Kronecker delta is just a way of expressing that. It's just sort of eventually you'll see how it shortens notation, but here it just makes it more complicated. But what this does is that whenever you see a Kronecker delta, it means set one of the variables equal to the other one. So here I have AJK equals a half M QJ dot QK dot delta JK. So delta JK tells me set J equal to K. So then I can rewrite AJK as AJJ equals a half M QJ dot times QJ dot. So it's just a way of me saying that I don't see any terms where J is not equal to K. And so I can keep the notation of having J's and K's separately, but then I multiply by this thing that if J and K are different, that thing is equal to 0. I don't know, that was maybe more confusing.
Yeah, that helps a lot, thanks.
Okay, thanks. Sorry. Okay. Any other questions? Okay. So if there are no questions, then we'll talk again on Wednesday. And yeah, so have a look at the assignment solutions and ask me if you have any questions. And please note that assignment 2 is now available. Thanks, everyone. Talk to you on Wednesday.